Good morning, afternoon, or evening. How y'all doing today? Welcome back to Morals Math Corner. Today we're going to be learning how to deal with complex rational expressions. So let's get right to it. First of all, a complex fraction or complex rational expression is a quotient or fraction that has at least one rational expression in the numerator and or denominator. Here are some examples of complex fractions or rational expressions. As you can see in this first complex fraction, we have a rational sum up in the numerator divided by a real number, so that meets the qualifications. In our second example, we have a sum of a rational expression divided by another rational expression, that meets the qualifications. And in our third example, we have the sum of rational expressions in the numerator divided by the difference of rational expressions in the denominator, which also meets the characteristics of a complex rational expression. Now, you have simplified a complex rational expression once the rational expression is in form n over m, where both n and m are simplified polynomials that have no common factors. That's when it's a simplified complex rational expression. Now, before we get into the crux of today's lesson, let's go ahead and just review dividing rational expressions. If you remember, in order to divide rational expressions, or to find any quotient for that matter of fractions, you want to use that good old stay, change, flip trick. And if you remember, stay, the first fraction or the numerator, stays the same. Change, you're going to change division to multiplication. And flip, you're going to flip the second fraction or the denominator in this case. So we're going to go ahead and flip it to its reciprocal. Once you've got that under wraps, second step is always to simplify. So I've got 5 over w plus 4 times, I can factor w squared plus 5w plus 4. How? What times what is 4, but when added together is 5. And the answer to that is 4 and 1. And now we can go ahead and simplify. So 5 goes into 5 one time, 5 goes into 15 three times, and the complete binomial of w plus 4 cancels out with the complete binomial of w plus 4 in the numerator, leaving me with w plus 1 over 3. All right, perfect. So I just wanted to review dividing rational expressions. So let's get to today's lesson. Simplifying complex rational expressions. There are two methods for simplifying complex fractions or complex rational expressions. I particularly like method 2, but I'm going to teach you both methods for all of the examples today so you can decide for yourself. So let's learn about method 1. In method 1, the first step is to add and or subtract both the numerator and denominator individually. Step 2, we're going to divide the rational expression. And step 3, as always, we're going to simplify the remaining rational expression. So let's get to it. In order to add and subtract both the numerator and denominator individually, we have to find the common denominator. So the least common denominator of the numerator is 6y. This first fraction is missing a y, so I got to multiply that to both numerator and denominator. This second fraction is missing a 6, so I have to multiply that to the numerator and denominator. So then I can have my numerator, the sum of the numerators, divided by the common denominator. Okay, for the denominator, in this case, it's pretty easy. We already have a denominator of 2, so we don't need to add anything. So we just simply place it here. And now, good old stay, change, flip. So the first fraction will stay the same. We're going to change division to multiplication, and we're going to flip the second fraction or denominator. And now we're going to simplify. So the binomial of w plus 6 cancels out with the binomial of w plus 6. 2 goes into 2 one time, 2 goes into 6 3 times, and I'm left with 1 over 3y. And that is method 1. Method 2 involves, first, finding the LCD of all the denominators. I like to call that finding the grand LCD. Then step 2, we're going to multiply the grand LCD to every numerator in both the numerator and denominator of the complex rational expression. And step 3, we're going to simplify the remaining rational expression. Okay, so let's check this out. How do we get the grand LCD? Well, we look at all the denominators. And the grand LCD in this case of 6y and 2 is going to be 6y. So step 2, I'm going to literally multiply the grand LCD of 6y over 1 to every single numerator. I'm not multiplying it to the denominator because I don't want to find common denominators. In fact, I want to eliminate the denominators. So what do we have here? 6y times y over 6, the 6's cancel, leaving me with y. 6y over 1 times 1 over y, the y's cancel, leaving me with a positive 6. And then 6y in the numerator times y plus 6 over 2. 2 goes into 2 one times, 2 goes into 6 3 times, and this is going to give me 3y times y plus 6. Don't multiply them yet. Leave it in factored form because then you can see how easy it is to recognize, hey, wait, I can now cancel the perfect binomial of 1 plus 6 and the other perfect binomial of y plus 6 in the denominator, leaving me with 1 over 3y, which is the exact same answer that we found using method 1. All right, let's continue. Let's get a little bit more complicated now. We're going to first solve this one with using method 1. So the LCD of the numerator here is y cubed. I'm missing a y squared, so I'm going to multiply that to both numerator and denominator because in this case I'm looking for a common denominator. And over here, y cubed is already y cubed, so I don't have to multiply it by anything, by 1 if you like. So you have 2y squared minus 8 over y cubed. Now, the LCD of the denominator, in this case, is y squared. So this first fraction already has the denominator of y squared. This second fraction needs 1 extra y, which I multiply to the numerator and denominator, leaving me with y plus 2 over y squared. Now I'm going to go ahead and stay, change, flip. So I'm going to stay. First fraction stays the same. I'm going to change division to multiplication, and I'm going to flip the second fraction. Now I'm going to go ahead and factor. So I've got 2 times y squared minus 4 over y cubed times y squared over y plus 2. And that's going to factor out to 2 times y plus 2, y minus 2. Hopefully you recognize there's a difference of squares. Over y cubed times y squared over y plus 2. And now we're going to simplify. The perfect binomial of y plus 2 in the numerator cancels out with the perfect binomial of y plus 2 in the denominator. I've got 2 y's in the numerator, which can cancel out 2 of the 3 y's in the denominator, leaving me with 1 y in the denominator. And now I have 2 times y minus 2 over y. And just in case you're tempted, no, you cannot cancel out the y in the numerator with the y in the denominator because the y in the numerator is attached to that negative 2. It's a polynomial. And you cannot cancel out individual pieces of polynomials. All right, let's check out method 2. Method 2 here, the grand LCD, in this particular case, is going to be y cubed. Remember that the LCD always belongs to the highest degree of any individual monomial or polynomial. So I'm literally going to multiply y cubed over 1 to every single numerator. To every single numerator. And again, why are we doing this? Because we want to cancel out the denominators. So I've got 1y in the denominator, 3 in the numerator, so that leaves me with 2y's in the numerator there, giving me 2y squared. And then I've got 3y's in the denominator, which cancels out with 3y's in the numerator, minus 8. In the denominator here, I've got 2y's in the denominator, which can cancel 2 of the 3y's in the numerator, leaving me with 1y, which I've got 2y. And then I've got 1y in the denominator, which cancels out 1 of the 3y's in the numerator, leaving me with a y squared. Now I'm going to go ahead and factor. I've got 2 times y squared minus 4. I can factor out a y squared here. I'm sorry, I can factor out a y, not a y squared. Pay attention, modal, which will leave me with y plus 2. Then when I continue to factor, I've got 2 times y plus 2 times y minus 2 over y times y plus 2. And now I simplify. So the perfect binomial of y plus 2 in the numerator cancels out with y plus 2 in the denominator, leaving me with 2 times y minus 2 over y. And once again, you can see that they have the same exact solutions, okay, using method 1 or method 2. All right, next, we're going to solve this one by using method 1. So for method 1, I want to add the numerators and then add the denominators first. So the LCD here of the numerator is x plus 2, which I'm going to multiply to both the numerator and the denominator here. And that's going to give me a 1 plus x plus 2 over an x plus 2. Over, coincidentally, the LCD of the denominator is also x plus 2, which I'm going to multiply to both the numerator and the denominator of the first fraction, which is missing that x plus 2. That's going to give me x squared plus 2x minus 3 in the numerator over the common factor of x plus 2. Now I'm going to combine like terms, clean it up a little bit. So I've got x plus 3 over x plus 2 divided by, let's go ahead and factor, I've got x plus 3 times x minus 1 over x plus 2. Now I'm going to go ahead and stay, change, flip. So that will give me stay, change, flip. So that should be a 3 there. And that's x minus 1. And then I've got my x plus 3 in the numerator cancels out with x plus 3 in the denominator. My x plus 2 in the denominator cancels out with my x plus 2 in the numerator, leaving me with 1 over x minus 1. All right, perfect. Now, let's go try this with method 2. For method 2 here, the grand LCD is x plus 2. So I'm literally going to multiply x plus 2 to every single numerator. Notice how I keep putting numerators over 1, like this x here. Why do I do that? Because that way I can clearly see where the numerator and denominator are, and I'm not going to get confused. That's a little pro tip for you. Okay, so what do we got here? We're left with the x plus 2's cancel here in the numerator and denominator, leaving me with 1 plus, distribute that 1, so I've got x plus 2 over, I'm going to distribute this x, giving me x squared plus 2x. The x plus 2's cancel here, leaving me with a minus 3, and that's going to give me x plus 3 over, factor this out, x plus 3 times x minus 1. The x plus 3's cancel out, and I am left with 1 over x minus 1, which again is the exact same answer that I got using method 1. All right, last but not least, let's solve this by using method 1. The LCD of the numerator here is going to be 3 times x plus 5. So I'm missing over here an x plus 5, which I multiply to the numerator and denominator. Over here on this side, I'm missing a 3, which I'm going to multiply to the numerator and denominator. And that's going to give me x plus 5 plus 3 over the common denominator of 3 times x plus 5. Divided by, I'm going to go ahead and multiply. I don't have to multiply anything, actually, because I already have a denominator of 9. So I'm going to go ahead and place that denominator down here, x plus 8 over 9. Now I'm going to do a little stay, change, flip action, giving me x plus 8 over 3 times x plus 5. Change the multiplication, flip 9 over x plus 8. The x plus 8 in the numerator cancels out with the x plus 8 in the denominator. 3 goes into 3 one time. 3 goes into 9 3 times, leaving me with 3 over x plus 5. All right, perfect. Method 2. For method 2, you got it. I got to find the grand LCD. So my grand LCD here in this case is 9 times x plus 5. So I'm literally going to multiply 9 times x plus 5 to every single numerator. Remember, we're doing that because we want to cancel the denominators. And my last one over here. All right, so let's simplify this. So 3 goes into 3 one time. 3 goes into 9 3 times, leaving me with a 3x plus 15. And then the x plus 5 cancels out with the x plus 5 in the numerator, leaving me with a plus 9. Over. The 9 in the numerator cancels out with the 9 in the denominator, leaving me with x plus 5 times x plus 8. Don't multiply these because you're going to have to refactor them anyway. I'm going to simplify here, going to combine like terms, giving me 3x plus 24 over x plus 5 times x plus 8. Going to factor out a GCF of 3, leave me with 3 times x plus 8 over x plus 5 times x plus 8. The x plus 8 in the numerator cancels out with the x plus 8 in the denominator, leaving me with the beautiful answer of 3 over x plus 5, which once again is identical to the answer that I found using method 1. So now you know method 1 and method 2. It's up to you to decide which one you love and then go ahead and master it. Thank you for watching. Come back anytime and take care now. Bye-bye.